Hi everyone, welcome to my talk. This is a cloud-based large terrain system for O3DE gems. I am Chen Wei and I am a graphics expert from Huawei. Although I can't meet you in person due to the current special situation, I still feel quite excited now as I am very honored to have this opportunity being a part of the first O3D conference. This talk will be divided into three parts. First, I will give you an introduction of our challenges and structures, followed by a demo session to show the current progress using the O3D engine. The final one will produce our future work. Here are some hot words you must have heard quite a lot these days, such as metaverse, user generation content, and digital cities, etc. These concepts are very popular as I believe it represents a trend to digitalize our current real world more and more into a virtual space. Well, no matter what exactly the form of this virtual world is, it is going to be big, to be nice, and to be fast. And a large terrain system will be somewhat involved or even a key component to a massive size virtual world. We believe the virtual terrain system, no matter for editing or rendering, it must contain these important requirements. First, it must be a real-time performance to provide a basic and a proper interactive experience for the users. And it must provide a good visual quality that at least not too bad to impede its marketing. It has a user-friendly editing and generation method. And lastly, it must be large, but not only in spatial size, but may also about maintaining a high fidelity in details, as it is a foundation for many other add-ons such as collision, vegetations, roads, rivers, etc. What makes it more challenging is the scale of the freedom. Here I put three images. From the left is a terrain visualization from a close view. It is important for the users to see the rock on the slope shiny and bumpy while facing to the light. They also need to give a good sharp edge detail. Then we zoom out a bit, like what the middle one shows here is an aerial view that shows a skyline of this mountainous area. The shape of each rock is no longer the focus. While the third image on the right is a space view. This makes the scene a lot different. It requires the terrain to be deformed into a spherical shape so as to highlight the light curve of the planet. Viewers may find them more interested in a continental coastline, which are completely different focus compared to the first close view interests. So this leads to a major problem that different viewing distance leads to various focuses with regards to all sorts of datasets and resolutions. Previously, an efficient blending and management of such a dynamic terrain system is highly integrated with the game engine itself. It is quite difficult to customize a terrain system in these engines as the data and asset structures had been specifically designed aligned with their own renderers. Now, O3DE is a new game engine, and it comes with an attractive concept, a modular system that tried best decoupling everything, such as this complicated game engine that aims to be gamified into solid gems as many as possible, even a renderer part. This gives us a new opportunity to try out a large terrain implementation that we have been struggling on some existing game engines. As previously mentioned about the scale of the freedom challenges, a continuous distance-dependent LOD is a must-have feature for terrain system nowadays. Without the CDLOD, the surface may look flat and boring, as what the red box indicates here. More specifically, a hierarchical data structure is unavoidable here. Both chord tree and clip maps have been quite popular. Each has its own advantages and disadvantages. For example, chord tree can dramatically reduce the number of required terrain blocks, which is very useful for viewing the landscape from a large distance. But tree construction performance is still relatively costly and have limits for those view detail representation. Clip maps has a fairly straightforward cost structure, which is easy to implement, but may lead to extensive blocks when viewed from a high distance. Well, we have implemented both structures individually and still busy profiling. It is likely that they can be combined and used in a more consistent manner. While the hierarchical data structure offers a high-level LOD control, the GPU nowadays is capable of providing a finer level of adaptive LOD. Tessellation shader is an ideal shader for terrain detail rendering when it comes out with DirectX 11. It does simplify the programming a lot and provide a compelling high-fidelity result together with a high-res displacement map. However, its performance is not the best, particularly when the tessellation scale becomes overwhelming. This may also be the reason that Atom Renderer is still missing this functionality at this stage. Therefore, we also implemented a vertex shader-based tessellation method. Similar to Unreal Engine, we bake the height LODs to the vertex attributes and calculates the interpolations and the offsets between each vertex during the runtime. Although the VS is getting bigger and fatty, the number of the new triangles is able to be limited and managed. The performance is then comparable to the Unreal Engine. What's more importantly is that the VS methods can be used in mobile devices, as it simply doesn't need the tessellation shader, which is very expensive on the mobile devices. Again, we are busy profiling these two GPU methods as well, although still have some problems for porting to the O3DE engine. Besides the CDLOD feature, the runtime also has a challenge to support the rendering of extensive landform materials. Basically, each set of landform material contains several texture maps, such as diffuse map, normal map, roughness map, and other texture maps that are based on PBR lighting standard. A block of a terrain area often holds more than one landform. As these two images showed here, it contains three different materials, which are dust, grass, and rocks. Each of them have at least 4 texture maps. To blend them together require an extra blending map, or what we call splat map, to hold the blending factors in its RGB channels. This easily occupies the texture slot usage up to more than 13 plus in the GPU's pixel shader. This is ensure that all these textures can be sampled and blended correctly in just one draw call. Keep in mind that the maximum number of texture slots is a very precious resource. It is a hardware limit and varies on different platforms from 8 to 32. It can be easily overwhelmed by landforms with many materials not even include the basic height maps and shadow maps requirements. To tackle this issue, there are 3 methods we are implementing and testing. First, using multiple splat maps, which are 4 channels each, to support up to 16 textures for each tile. Texture Atlas is also implemented to help the support for more materials. The performance is good if the GPU has a good bandwidth. However, artists may spend more time to carefully balance the texture slot usage and visual quality. Secondly, we also implement an overall ID map plus weight map method as used by Lumberyard, so as to reach up to 127 materials in total, but only 3 blends for each block. We found its performance is lower than the first method, but requires less bandwidth. Third, we are currently working on a virtual texture implementation in runtime. This aims to minimize the memory usage while still providing a high quality, particularly for close view details. The third major challenge is the data size limit, particularly for the super large terrain dataset. For instance, if I remember correctly, the Microsoft Flight Simulator has up to 2 petabyte data in total, which is impossible for any consumer devices to handle locally. Cloud streaming service aims to solve this issue. It can manage the storage usage through a local data pool control. It can also shift some of the runtime workload to the cloud, such as asset packaging and tree updating. This enables a balanced quality and performance experience across multiple devices or platforms. And this can also be very helpful to provide a much smaller package for easier distribution. The diagram here indicates the workflow of the cloud and client coordination. Start from the camera status updating. The cloud server can do some scene synchronization with its high-fidelity asset database, such as packaging and streaming the required data in a parallel manner. The client side is still responsible for main rendering task. It contains both a low-quality asset pool and a high-quality pool that have different focuses. The low-fidelity assets pool provides the renderer with immediately requested low-quality assets, so as to guarantee the real-time performance, while not causing any broken pictures. This pool shall be updated infrequently, as they are basic rough assets and supposed to covering a large area that doesn't change too often when the camera moves. On the other hand, the high-quality assets pool shall be updated frequently from the cloud side, so as to provide a higher quality based on the view status changing. They only start rendering when they are fully streamed. A lagging or popping may occur, but many tricks such as dithering or blending can help to mitigate the artifacts. Here I list our terrain framework in an overall view. Similar to many existing game engines, it can be divided into 2 parts, which are the editor and the runtime modules. The editor module takes in the raw assets from external DDC softwares such as Word Machine, Word Creator, or Houdini, etc. Their exported raw assets are digested in an editor mode on a separate thread, following the O3DE's asset builder mechanism. In the meantime, the terrain editor provides various methods to adjust the terrain properties, such as manually sculpting the high data using a fine brushing control style, or simulating a natural evolution using a general procedure method, such as the GPU-based hydraulic and thermal erosion evolution. These methods are not only applied to the height maps, but also can be leveraged to material editing. In the editor mode, the terrain tile data can also need to be managed and tuned to meet requirements for the balance between performance, quality, and functionalities, such as many add-on attachments and generation. The key is the user's workflow must be intuitive and efficient. The runtime module contains a data streaming service for the cloud and client coordination, as I explained previously. We also include an asset partitioning system to best utilize the memory usage of streamed data. The tile processing part is a hierarchical data structure, as I mentioned earlier, to provide a higher level LOD support. The rendering system is converting the raw data and generating the job commands aligned with the correspondent rendering data structure, such as buffers, textures, and pipelines, etc. In the O3D's Atom renderer, a terrain feature processor needs to be applied. We have to add some tessellation support in this version to test our GPU CD LOD function. In general, the editor and the runtime module can be either in its own gems or merged into a big one. The communication between them is through a terrain E-bus, which is derived from O3DE's well-established AZ framework. Frankly speaking, the entire terrain system is quite huge, and so far we are focused more on the runtime part, simply because it is more fundamental, as it needs to be used both by the final runtime rendering and editor's viewport service, which is shown in the middle of this diagram. Next, I'm going to show some demos. Start with our initial close encounter with O3D engine. This is our current progress of terrain integration to the O3D engine. So far, we are based on the O3D's July version 2107. So many new features from the development branch are still missing here, includes the landscape canvas. As you can see, our terrain module can be enabled simply by adding a component. Here, you see it supports the height data import from an external image file. While it still looks black because the scene is still missing a light source, we have linked the shading of the terrain with Atom's default PBR pipeline, so the light properties, such as the direction, intensity in a scene, can directly applied to our terrain module. As you can see, it is busy rotating the directional light to affect the terrain's shading color. Here we implemented a basic terrain editing interface, as you may be very familiar with. Mimics the lumberyard style. We also have implemented some basic height modification methods, such as using the brush style to rise and lower the landscape. The radius, hardness, and height are the only available brushing controlling params so far. At least it enables the real-time height map modification for the users. As you can see, the user is lifting the terrain intuitively. Here, the user is creating another terrain instance, although it is not automatically translated in a tiling style. It forms the foundation for future tiling system. Unlike the previous demo, which has a quite common workflow for terrain editing, the second demo is about some structure level exploration. It requires to inspect new methods in an agile development style. While exploring new techniques directly on the O3D now is not that convenient, as this age engine is still in a very early stage. So we are working on other POC implementation in a parallel manner. Here is a demo that we are testing our country data structure, the use of tessellation shader, and the cloud streaming mechanism for a large terrain area. This terrain covers 16 by 16 square kilometers, which contains about 5.4 gigabyte data on server that includes all LOD levels and materials. This is still an early stage, as we are aiming to define a better tile structure so as to balance the quality and bandwidth requirements. But at least from this demo, we can see the number of tiles with various LOD levels are loading and rendering asynchronously. The different color bands indicate the different LOD sections from the country structure. It is pleased to see a very smooth visual transition between the LOD changes. And please note that the bottom lines in the UI shows the streaming situation. Currently, the height map, normal map, and the weight maps are keep accumulating in the local asset pool. And now we are slowing down the camera and going to have a close look on the GPU tessellation effects through the wireframe mode. By tuning the tessellation factor, the number of small triangles does become overwhelming. Well, the tessellation does provide a compelling visual result, particularly good from a close distance. Besides the help from the tessellation, this terrain covers 16 different material sets. Each consists of 4 textures. It is implemented using multiple spline maps method. This demo also proved that the transition can be smooth between LOD changes under the current streaming mechanism. So, besides the using of tessellation shader, which may deteriorate the performance from the extensive small triangles, what are the other options to produce the similar adaptive vertex morphing method? Another separate prototype work is the vertex shader-based CDLOD. We found one of the big terrain differences between Unity and Unreal is the vertex morphing. We also believe this is one of the core reasons leads to a fundamental quality and performance gap, particularly on mobile devices. As you can see from this demo, it is a map of 248 tiles. The morphing occurs with smooth interpolation only on a vertex shader, so no tessellation shader is required. Hopefully, this can provide a good performance together with a visual quality no worse than Unreal with regard to the vertex manipulation. We are still busy debugging and profiling. Hopefully, it can be done before the end of this year, so we can have a terrain in O3DE with a competitive performance compared to U engines. For a quick summary, we have developed a terrain module that integrated with O3D engine through GEM. We provide a basic terrain construction and rendering mechanism. We are also exploring streaming methods to support large terrain visualization with extensive materials. CD-LOD exploration are also undergoing for better performance and quality balance. Frankly speaking, there are quite a lot of work need to be implemented for future work if the terrain system aims to be a comprehensive one. We are not able to provide a full roadmap yet, but here are some aspects that have a higher priority. The first part is the continuous learning and development using O3DE engine. During our development, we enjoyed the modular concept, such as how helpful the feature processor is to decouple the terrain module from the engine. But due to the shortage of learning materials, such as the shortage of function samples and guidance, the O3D engine learning curve is still quite high. This becomes more challenging when working on the low-level modulars, such as the use of atom renderer. Thanks to the opportunity offered here, we would like to deepen the cooperation with O3D team. Furthering the development in O3DE will be a major method to flatten the learning curve. For instance, porting demo features to O3DE engine is very helpful to understand the germ system. Further exploration will be continuously conducted. The performance and the quality balance remains on the top of our list. We will keep optimizing the stream mechanism so as to support the size of a digital city in the near future. Virtual texture and decal rendering will be critical to provide a high visual quality. However, they are closely related to the renderer capability, which again may need close cooperation with the O3D team. We are also interested in terrain generation, particularly in large-scale simulations. We firmly believe that an easy workflow is critical to the success of large terrain editing. Natural evolution simulation and AI-assisted methods are definitely the way to go. Many of the add-ons are a must-have component for game engines, such as the collision, roads, and vegetation, etc. They can be implemented in separate modules and linked to the terrain using eBus system. We will start with the basics to support our requirements, as well as strengthen the connections with all of you here, simply because for a new game engine, there are too many modules to cover by a single team. And with this, it is the end of my talk. You are welcome to share any questions with me through the email. I really like to hear from you. Cheers!